So this will be the third lecture from chapter 21, so this will be the last lecture in chapter 21. So in this lecture we'll look at how amides are made and the reactions that they undergo, and look at how nitriles are made and the reactions that they undergo, and then just remind ourselves of the spectroscopy of these different molecules. Okay, so how to make amides. So no new reactions. We looked at all of these reactions in previous lectures. So if you take a carboxylic acid and an amine, so similar to a Fischer esterification, right? You can lose a molecule of water. Again, that's not the mechanism, it's just a way to think about predicting the product. So you make an amide in water. Or if you have an amine and an acid chloride, then you lose HCl. And make an amide in HCl. Again, that's not the mechanism. The mechanism is similar to mechanisms we've looked at in previous lectures where you make the tetrahedral intermediate. Or if you have an amine and an anhydride, right, again, so you lose a carboxylic acid and then this nitrogen would end up in its place, and whatever's attached to nitrogen is just along for the ride. Right, so carboxylic acid side product. Or if it's an ester, so however many hydrogens are on nitrogen, you need at least one. Then that will end up with the leaving group, and then the nitrogen and everything else attached to it will end up on the C double bond O. So again, an amide, and now your alcohol is your leaving group. Okay, or this would be just a slightly more complex example of this first reaction, carboxylic acid and an amine, if they happen to be in the same molecule. Right, then you can make a molecule of water, and this nitrogen would end up attached to that carbon. So that would be a 1, 2, 3, 4, 5, 6 membered ring where nitrogen is part of that ring. Right, so 6-membered ring, nitrogen is part of the ring. We call nitrogen atom number 6. So if we call that 1, 2, 3, 4, and 5, then number 1 is a C double bond O. The OH is gone because it made a molecule of water. Nitrogen still has a hydrogen left on it. Number 5 has a methyl group, and 2, 3, and 4 are just CH2. So you would make that cyclic amide, which, if you remember, that is called a lat 10. Okay, so that's how you make amides, and then we'll look at just a few reactions that they undergo. So again, amides are pretty stable molecules, pretty stable functional groups, so they're not very reactive. So if you want to make them react, you have to beat on them a little bit. So if you react them with water, then typically you would have to use acid catalyst or a base catalyst and heat to make them react. But this basic reaction is just a molecule of water, right, attacks and kicks that off. That's not the mechanism. Again, that's just a way to think about how to predict the product. Oh, sorry, the nitrogen is now gone. So OH ends up in its place. And then you would have an amine side product. Right, or if it's hydroxide, then hydroxide would attack here and kick that off. And the only difference being here, since that's a carboxylic acid, and if it's in the presence of hydroxide, which is a base, then hydroxide would deprotonate the carboxylic acid. So you would technically end up with the conjugate base of the carboxylic acid plus the amine as your side product. And in a previous chapter, we looked at how amides react with lithium aluminum hydride. So if you remember, the way that they react is the C double bond O goes away. So different than esters, right? The nitrogen does not leave in this case. The C double bond O just gets reduced all the way down to a CH2. and nitrogen is still present. Okay, so that's all the reactions of amides we're going to look at, how they hydrolyze and then how they reduce. Okay, so so if we did this reaction, so if we had that lactam with lithium aluminum hydride, so if you reduce the lactam with LAH, it's not like an ester lactone, right? The ring would stay intact because all you do is reduce the C double bond O down to a CH2. Okay, so for nitriles, how to make nitriles. So we've already seen several reactions that make nitriles. So this was an organic 1. So you can make them through an SN2 reaction. CN's a good nucleophile, so that can attack here and kick the bromine off. And you've got the nitrile. We looked at this in the aldehyde chapter. Right, that would make a cyanohydrin. And a different recipe that's safer rather than working with toxic HCN gas is use sodium cyanide and HCl, but it's the same concept, it just makes a cyanohydrin. And then in chapter 19, amine chapter, we looked at the diazonium. If you make diazonium with copper cyanide, right, then you can substitute in 2 gas and make the nitrile. Okay, so we'll look at a couple of new reactions of how to make amides. So we're not going to go through their mechanisms. So if you take a primary amide, so the nitrogen's got to have 2 hydrogens attached, and you react it with P2O5 or P4O10. These are dehydrating agents. Right, so they'll make the molecule lose water, so this is going to lose a water molecule, and then you'll have a CN triple bond instead, so that'll make the nitrile. Or if you take a primary amide with SOCO2, thionyl chloride, or POCl3, that'll convert this into a nitrile. And again, so we're not going to go through the mechanisms there. So just some reactions for you to remember. So the carbon structure doesn't change at all, right? Just take that amide and convert it into a nitrile. Okay, and then regarding reactions of nitriles, so we've looked at 4 reactions before, and we're only going to look at 1 new reaction. So if you take a nitrile with H2OH plus and heat, so acid hydrolysis, so we looked at this in the carboxylic acid chapter, so we looked at the mechanism there. So if you remember, that's just going to cleave off ammonia, and then that carbon gets converted to carboxylic acid. So you'd make ammonia and carboxylic acid. And if you did base hydrolysis, so this is acid hydrolysis, if you did base hydrolysis instead, so base and water, so it's similar. The only difference being, so the nitrogen's still going to go away as ammonia. The only difference being, since carboxylic acids are acids and this is hydroxide present, then those will undergo an acid-base reaction, and you would technically get the conjugate base of the carboxylic acid. Right, so you would make the conjugate base of a carboxylic acid and ammonia. But again, it's just that carbon is being converted either to a carboxylic acid if it's acid hydrolysis, or a carboxylate, the conjugate base of a carboxylic acid, if it's base hydrolysis. So in the amine chapter, we looked at how nitriles reduce with lithium aluminum hydride. Right, so you're just going to add H and H and H and H across the triple bond, whether you use H2 and palladium, H2 some metal catalyst, or lithium aluminum hydride and water. It's just going to reduce the amide or the nitrile to a primary amine. So you reduce the triple bond to single bond. Okay, and then one new reactions of nitriles that we'll look at. So if you take a nitrile and react it with a Grignard reagent, so that carbon's partial positive, that carbon's partial negative. So you're going to take the 2 electrons in the carbon magnesium bond and use them to make a bond to that carbon and break the triple bond. So nitrogen's now got 2 lone pairs, so if you calculate the formal charge on nitrogen, it's -1. And then that's all that's going to happen. So you're done after step 1. So now you do step 2. So now you react this with a dilute acid and water, so N- picks up a hydrogen, and now what you have is an imine. And if you remember imines, if you react imines with water, so this is back to chapter, the aldehyde ketone chapter. If you react an imine with water, you'll regenerate the C double bond O, and the amine will come off. Right, so that will remake the ketone, and then you would have ammonia come off of the molecule as a side product. Okay, so hopefully you can see that predicting the product there is easy. So if we did this reaction, right, or how to see the product, if you just recognize the reaction, so nitrile plus Grignard reagent should make a ketone. So we're just going to take whatever's attached to magnesium and stick it here, and then this carbon is going to become a C double bond O, and then that's going to go away as ammonia. All right, so that carbon of the nitrile will now be a C double bond O, and it'll have whatever Grignard reagent alkyl group or aryl group attached there instead, and you'll make a ketone. Mechanism's a little bit harder, right? If we had to sketch through this mechanism, something that we talked about in the aldehyde ketone chapter, it's a lot of steps in that mechanism, but it's a mechanism that you should know how to work through. It was on the last exam. Okay, so that's it for the reactions of this chapter 21. So let's apply these reactions and do a little bit of synthesis. So if we take benzene, how do we make these 2 molecules from benzene? Okay, so we know how to make amides. So how do we make amides? So if we had that acid chloride and we had that amine, they would react with each other to make that amide, right? Okay, so how do we make acid chlorides? Well, so how do we make acid chlorides from carboxylic acids? So if we had that carboxylic acid with SOCO2, we could make the acid chloride. So how could we get this carboxylic acid? Well, if we had an alkyl group on benzene, we could oxidize it, right? CaMnO4 would oxidize, as long as that carbon has a benzylic hydrogen, it will oxidize to benzoic acid. And then how can we get a methyl group on benzene? We could do a Friedel-Crafts alkylation, and now the synthesis is done, right? So as long as we use benzene, we can use whatever else we want to use in the synthesis, which means we don't have to show how to make the amine or anything like that. We just have to use benzene in our synthesis and anything else we need to get to the product. Okay, if we want to make this from benzene, how could we do this? So let's see. We can make esters. How can we make esters? So if we had that carboxylic acid And this alcohol, we could do a Fischer esterification, right? And how could we make that carboxylic acid? Well, if that was a nitrile there, if we had that nitrile, then we could do acid hydrolysis and convert the nitrile to a carboxylic acid. How could we get a nitrile there? Well, if there was a leaving group there, then we could react that with KCN and do an SN2 and substitute bromine with the CN. How could we get the bromine there? Well, if we had propylbenzene, we could do MBS CCl4 in light or heat and do a free radical bromination, right? Or we could do Br2. Either one is fine. You don't have to show both, you just have to show one. Right, you just have to show one sequence of reactions that work. And then how could we make propylbenzene from benzene? Well, we could do a Friedel. Ooh, that's a little bit more challenging, right? Because we had to avoid carbocation rearrangement, so we could do Friedel-Crafts acylation. So we could put the ketone on and then reduce the ketone to the alkane. That way we don't have to worry about Friedel-Crafts, the Friedel-Crafts alkylation carbocation rearrangement. Okay, so that's a long synthesis, but that incorporates a lot of reactions that we've covered this semester. And so, yeah, anytime, so third exam, fourth exam, you could expect a synthesis problem at least 3 or 4 step synthesis. Okay, and then lastly in this chapter, let's just remind you some of the spectroscopy. So 5 different derivatives in this chapter: the acid chlorides, anhydrides, esters, and amides. They all have C double bond O. And so if you remember, C double bond O region is typically 1800 to 1700 in IR spectroscopy. So the acid chlorides are around 1800 for the CO stretch. For the anhydride, there's 2 peaks in that region. So around 1800 and 1750, you see 2 different C double bond O stretch, one symmetric and one asymmetric. For the ester, around 1730, and for the amide, around 1640 to 1680. You know, why is it at such a low wave number? And it's because amides have this resonance form, which is a significant resonance contributor, and so there is some single bond character to that double bond. And if you remember, CO single bond is around 1200 inverse centimeters. So because this has a significant resonance structure that has some single bond character to that CO double bond, it's at a lower wave number. But the point is, they all have a C double bond O, so in that 1700 to 1800 window, you can expect a CO stretch. And for the nitriles, the triple bond, if you remember, they have a signal around 2200 inverse centimeters for the C and triple bond stretch. So easy to tell if you have a nitrile in the molecule, right? Because in that IR spectrum, typically a pretty intense peak around 2200 for the C and triple bond. And CO double bond stretches are pretty intense as well. And then lastly, for carbon 13 NMR, there's a pretty characteristic signal, right? For C double bond O is around 170 to 180 for any of these derivatives. Okay, so that's it for chapter 21.